Welcome to the Organic Chemistry Podcast, Dr. Brian Lloyd's scribblecast of organic chemistry lectures and solutions to homework problems. In this Organic Chemistry scribblecast lecture, we're beginning to look at alkenes and alkynes. If you recall, alkenes are molecules that possess sp² hybridized carbons. They have a sigma bond joining the two carbons and one pi bond, pi meaning side-to-side overlap of the two p orbitals. The shape around the carbon of the blue orbitals is trigonal planar. Alkynes possess sp hybridized carbons, a sigma bond, two pi, 2p, 2p bonds, and have a spatial relationship that was referred to as a linear shape. Alkenes are referred to as double bonds, double bonded carbons. Alkynes are triple bonded carbons. We're going to begin our examination of alkenes and alkynes by considering the differences in acidity. Now, organics normally aren't considered acids, but they do vary between themselves in terms of acidity. They're not hugely acidic. If I take the simplest alkyne, ethyne, and I compare it, say, to ethene, and I compare that to ethane, we can calculate the following Ka values. So if I was to write a Ka, the Ka is approximately 10 to the minus 25 for an alkyne, 10 to the minus 36 for an alkene, 10 to the minus 42 for the ethane. If I convert that to pKa's, the negative log of these values, well, that's just 25, 36, and 42. Lower pKa's, larger Ka's are stronger acids. We observe that according to these values, alkyne is a stronger acid than alkene. Likewise, alkene's a stronger acid than ethane. How strong is the acidity of the alkyne? Say, compare it to water. Water is considered fairly neutral. What's the pKa of water? The pKa of water is around 15. The alkyne is significantly less acidic than water. So as far as acids go, water is more acidic than the free alkyne ethyne. But how do we explain this trend? Well, it has to do with orbital size. If you recall, alkynes have sp hybridization. Alkenes have sp², and alkanes have sp³. Our percent S character in these orbitals is 50%, 33%, and 25%. Now the S orbital is less diffuse than the P, which means the sp, because it has more S character, is smaller. What does that mean? Well, when we pull an H off, when we actually build the anion, the lone pair will exist in an orbital whose hybridization will depend on whether you have an alkane, an alkene, or alkyne. In the case of alkene, you'll be in the sp² orbital. In the case of alkyne, you'll be in the sp. But the sp orbital is smaller. It's closer to the nucleus. This is akin to being more electronegative. Why? Well, what do more electronegative atoms do? They pull harder on electrons. They hold electrons closer. Closer to what? Well, closer to the nucleus. Being more electronegative is like having smaller orbitals. These electrons are held closer to the nucleus. When you hold electron density closer to a nucleus, when you're more electronegative, you stabilize a negative charge. So the alkyne's more acidic because the anion that forms is more stable. The anion is more stable because the lone pair is in a smaller orbital, which is like being more electronegative because the electrons are held closer to the nucleus. Because it's better able to accommodate the negative charge, the alkyne's more acidic. Okay. Now I can draw a reaction to prepare this. Let's do that. I can take alkyne, for example, and I can react it with some base. I'll just call the base B with a lone pair, B minus. And that'll set up an equilibrium, which will give me the anion. And BH, the base has grabbed the proton, and because it was negative, it's now neutral. Okay. Because this anion is most stable of the three alkyne, alkene, alkane, this anion forms more readily, which means the equilibrium shifted to the right, which means the alkyne is more acidic than the rest. Although this alkyne is a weaker acid than, say, H2O, he is a stronger acid than NH3. Now, NH3 is not a very strong acid at all. It's recognized as a base. But the point is, you could pull H's off NH3 and make NH2 minus. And the point is, it's easier to pull an H off an alkyne than it is off of NH3. Now, the last thing to note is the product anion is referred to as an acetylide anion. And they are good nucleophiles. This is a new nucleophile. It's not on the nucleophile list you've learned already in the course, so you can add it. But it is a relatively good or strong nucleophile. It's a good nucleophile. Okay. How do I prepare the acetylide anion? What kind of bases must I use? Well, this is similar to what we covered in the alcohol. It is very similar to deprotonation of alcohols. You could use sodium hydride. Sodium hydride is a source of H minus. Has a lone pair. H does not like a negative charge, and so H minus can grab an H plus. If it does, it very quickly goes to H2 gas. You get H2 gas. But H minus is very basic, more basic than alkyne, so sodium hydride can be used here. And then the BH would be H2. Alternatively, as we pointed out, NH2 minus is a more powerful base, so we could use sodium amide. We could use NH2. This molecule has two lone pairs. It would grab the proton and become NH3. We could use Grignard reagents. Grignard, GR, Grignard reagents. Molecules like methyl, magnesium bromide. But we could use any alkyl, methyl magnesium iodide, for example. We could use ethyl, propyl, phenyl here. The point is when the carbon's attached to magnesium, you get a delta minus. And the delta minus on carbon makes the carbon very basic. It would grab a proton. In this case, if H plus was added, you'd get methane gas. And that would usually bubble out a solution. And you get the acetylide. You also can use sodium or potassium. Now, when we use sodium and potassium, we get the exact same reaction that we got in the case of alcohols. What do I mean? Well, in alcohols, we wrote down an ROH. Well, instead of the ROH, we have the alkyne. Okay. I believe we used ethanol in a previous scribblecast lecture. And then I hit this with sodium metal. Well, this produces sodium, in the case of ethanol, ethoxide, but here it produces a sodium acetylide, which I draw like this with its lone pair. There's a minus, sodium plus, and we lose 1/2 H2 gas. And of course the gas bubbles out of solution, so the arrow up means it bubbles out of solution. And now how does this reaction happen? In actual fact, you must use 2 sodiums for this reaction to occur. Just like we did in alcohol. Now what I'm showing you is the mechanism of how the top reaction occurs. The 2 sodiums want to lose electrons. They want to become sodium pluses to get noble gas configuration. Those 2 electrons add to the carbon hydrogen, this CH bond. Now if the CH bond breaks homolytically, you get 1 electron on each. You get radicals. The 2 electrons from sodium go into antibonding levels, causing the bond to break. And one of the sodiums gives 1 electron to one atom and 1 electron to hydrogen. That means the carbon and hydrogen both got an extra electron, so they both become negative when the bond breaks. That result is the negatives associated with the sodium pluses. So the 2 sodiums make the acetylide anion, and you get sodium hydride, which is sodium plus H minus. Now, you don't have to show the plus minuses. I'm showing them so you know the charges and there's no confusion. Now, that doesn't look at all like the top reaction. But you may remember sodium hydride was a powerful base as well. And there's lots of alkyne around because you bubble it through the solution with the sodium in it. So what's going to happen then is the sodium hydride is going to attack. Now I'm not going to put the sodium plus H minus this time. This is how you draw it normally. But you know sodium is positive, H is minus. The H minus will grab an H plus off the alkyne. And this time, when the H minus grabs an H plus, you get H2 gas. Well, that still doesn't look like the top reaction, which bubbles out solution. So I can add these 2 equations up. I get 2 ethynes plus 2 sodiums plus sodium hydride. Give me 2 sodium acetylides. Okay. We'll get H2 gas, which of course bubbles out of solution, and plus sodium hydride. Now when you have 2 identical groups on either side of the arrow in the equation, mathematically they can be subtracted from both sides, so they cancel and you've got the same equation. Now you notice that this equation is the same as the top except both sides were divided by 2. Ooh, I forgot my 2 here. There were 2 of those. So there you have it. Even sodium or potassium metal can be used to deprotonate the alkyne. Let's press on now and take a look at how alkenes are prepared. In many ways, this is a total review of the alcohol section. Preparation of alkenes. Okay. Well, obviously the first part is dehydration of alcohols. We've done alcohol chemistry. we can dehydrate or remove the OH group from alcohols and make alkenes. This is called an elimination reaction and proceeds either by E1 or E2 depending on the alcohol. We require acid to make a good leaving group. And because we get more stable carbocations for E1, or we get more stable alkenes in the transition state of the E2, tertiary occurs faster. Tertiary's faster than secondary, who's faster than primary for elimination. And this is a standard rate in elimination. The reaction with primary alcohols is slow because they're less substituted alcohols. They're less stable. Remember Zaitsev elimination? The more substituents off the carbon-carbon double bond, the more stable the double bond, the faster it forms. Well, if you have a primary alcohol, like ethanol, you're not going to get a double bond with any substituents off of it. Energetically, this is a higher energy double bond. Now, when we react in an acid, we don't go E1. We don't go E1. We go E2. Why? If we went E1, when we protonated, and we got a good leaving group, and then that leaving group left to make carbocation, we'd get a primary carbocation. Primary carbocations are too high energy. They're too unfavorable. And so what happens is this reaction does not go E1. So it goes E2. E2 requires anti-periplanar elimination. So this H rotates anti. Our base, because of the protonation, we now have HSO4-, so I'll draw it up here. If there's some water around, we may get that. HSO4- comes in and grabs the proton. The electrons form the pi bond, and this leaves. Now, in order to get this unsubstituted alkene, we really have to heat it. We have to go to 180 degrees Celsius. We've also discussed this in the alcohol section. And so E2 elimination occurs, anti-periplanar elimination, and we get ethene. High energy, not easy to do. So primary alcohols are slow, but primaries go E2. And if you recall, that's very similar to what we had for alkyl halides. Alkyl halides all prefer E2. But what about secondary and tertiary alcohols? These guys go E1. And you might be saying to yourself, why? All alkyl halides go E2. Why, when you get to alcohols, would E1 all of a sudden become favored for tertiary and secondary? Because in alkyl halides, the favored elimination for tertiary, secondary, primary is E2. Well, this has to do with one of the key features of the E1. Actually, one of the last statements, the favored by statement. E1 reactions are favored by weaker bases, higher temperatures, and polar product solvents. Look at what you're reacting in with an alcohol. In alcohols, you got to react in acid. Acid makes water look positively nonpolar. Acid ionizes, producing extensive ionization in aqueous media, unless it's in pure form, and it maximizes the polarity of the solution, giving a huge boost to E1. So where in alkyl halides you only can use the most polar solvent you can use to dissolve an alkyl halide is a water-alcohol mixture. And compared to an acid, that's extremely low polarity. So because of polarity, carbocation formation is not very favored. And so all of the alkyl halides go E2, pretty much. There are exceptions in benzylic and allylic resonance stabilized cases that we will look at later on. But for alcohols, polyprotic solvents help solvate better carbocations, favoring the formation, speeding up the E1 reaction. And so tertiary and secondaries go E1 because you're in this acidic media. Let's look at some reactions. So now we're going to do secondary alcohols. We're going to look at several secondary alcohols as examples. The first one is going to simply be a ring structure with an OH. Well, as usual in cyclohexanol, I need some acid to make a good leaving group. OH is a poor leaving group. We need to protonate the oxygen to make a better leaving group. You can use sulfuric acid. You also can use, let's use phosphoric acid this time. I get the good leaving group. The good leaving group leaves, so minus H2O. H2O is pulled off. And I get a carbocation. Always, always, always check for 1,2 shifting in carbocations. This is a secondary carbocation. If I shift an H, I must keep secondary, so no shift occurs here. And this H is here that I can pull off of beta carbons. Beta carbons, remember, the carbons next door to the positive charge. The carbon bearing the OH or the H2O plus or the plus is referred to as the alpha carbon. You have to pull beta H off because you pulled the OH off. To make a double bond, you got to pull one group off one carbon and another group off another carbon because a double bond extends between two carbons. So our base will come in very quickly and pull one of these H's off. Okay. In this case, our base would be H2PO4 minus. And it could come and grab a proton, and these would make your pi bond, and you'd get this guy for your product, cyclohexene. If you have a more substituted alcohol, say you have cyclohexanol and you have a methyl here, this time, let's use H2SO4. Well, you get the same thing as last time, except you have a methyl here. You get your protonated group. You minus H2O. Got the 3 on my CH3. And you produce your carbocation. Again, this is a secondary carbocation, and what you must do, of course, is be very careful. You must check for 1,2 shifting. There's an H here. If I 1,2 shift that H, so I do a 1,2 hydrogen shift. I get this guy. And the plus is right there. So the plus shifts to this position, right here. Put a dot on the carbon. Okay, now we're looking for beta hydrogens. Let's draw this a little larger if we can. We have CH3 here. We have the plus right there. There's our carbocation. We've gotten a tertiary. We shifted from a secondary carbon to a more stable tertiary carbon. We must now look for beta hydrogens. Well, we've got hydrogens here that are next door to the positive. They're beta. We've got hydrogens here that are next door to the carbon. They're beta. And actually, if I pull off either H from either of those carbons, I will produce this alkene. Okay, so if, say, I use, as I'm in H2SO4, so my base now is, what, HSO4 minus? So if HSO4 minus comes and grabs one of these H's, like here, if it comes in and grabs one of those H's and those two electrons go here, I will get this alkene. Name that alkene. That's 1-methylcyclohexene. If I form the double bond on the other side, I still have 1-methylcyclohexene. So pulling off either of those H's from either side makes the same alkene. If I actually drew it, the other alkene, it looked like this. These are both 1-methylcyclohexene. They're the same molecule, they're just flipped. So I don't need to draw that. Okay? But there is another source of beta hydrogen. There's another beta carbon. This carbon's beta to the positive. This carbon's beta to the positive. But so is this carbon. I could pull an H off of that and move the pi bond. He could grab an H off there and give me a pi bond, in which case I would get this. Now that's a different molecule. And one could ask who's major, who's minor, and apply the Zaitsev rule. If I look at the double bond here, the dots show the carbons of my C double bond C. How many carbons attach to that C double bond C? Well, there's one here. There's one here. And there's one here. There are 3 substituents off that carbon-carbon double bond. If I check my double bond here, I've got here and this carbon as part of the double bond. I've only got 2 substituents off of this one. 3 substituents is more substituted. According to Zaitsev rule, more substituted is more stable, and when the more stable is major, you're following Zaitsev elimination. That's the usual form elimination takes place. So indeed, this more substituted one is major, and he is minor. Okay, let's look at one more elimination from secondary alcohols. And because it is E1, let's draw it out stepwise, as we would in a proper stepwise mechanism. Clearly, each of these arrows represents a separate step, and it's a quick shorthand to write it out. But you also can write out and title each step as well. For example, in the E1 elimination of this molecule, step 1, of course, with alcohols, is always protonation. Protonation to produce a good leaving group. The OH lone pair picks up a proton. So let's try again with another secondary alcohol. I'm going to just put H+. Could be using H2SO4, H3PO4, but you get some H+ and you protonate the alcohol. Yeah. Excellent. We've got a good leaving group now, so we can begin our second step. Step 2. Remember what it's called for the E1? Step 2 is called ionization. It's also called what? It's also called carbocation. Formation. I get this carbocation. Now, whenever you do SN1 or E1, whenever you get a carbocation, what do you have to look for? You have to look for rearrangement. So step 3, check for rearrangement. Rearrangement if possible. Key feature of the SN1 and E1 reaction mechanisms. Okay, so rearrangement, draw a carbocation again. You have to ask yourself, what kind of carbocation do you have? Clearly, I have a secondary carbocation. And I can do a 1,2-methyl shift. If I do a 1,2-methyl shift, I get this carbocation, which is tertiary. 1,2-methyl shift from secondary to tertiary. Is tertiary more stable? Indeed it is, so this 1,2 shift happens. Step 4 now is base attack. The base depends on what acid you used. If you use a sulfuric acid, since you took a proton off to protonate, the base is HSO4-. If you use sulfuric acid in water, it's possible for water to be the attacking base. We must find the beta hydrogens. These are the hydrogens off the carbons next door to the carbon who bears the positive charge. So we look at our positive charge right here. And we say, where are the beta carbons? Well, the beta carbons are here, here, and here. So the hydrogens off of those carbons can be pulled to make an alkene. So we've got basically hydrogens on the methyls. Indeed, if I pull an H off either of the methyls, I will produce a double bond. A double bond that gives the same alkene. So whether I have this guy with the double bonds to the left, or I made the double bond up and down, it would be the same molecule. Or I could pull this H off, right here. If I pull that H, I'll put a double bond here, and I'll get this alkene. Who is major and who's minor? Well, I could draw a red line under the double bond. How many substituents are attached to the carbon-carbon double bond in the top molecule? Well, I have the methyl and the isopropyl, 2 substituents. How many substituents are attached to the carbon-carbon double bond in the lower molecule? Well, I have 4 methyls, that's 4 substituents. Indeed, the top molecule is minor with less substituents, and the bottom is major. Now there's an excellent experiment that you can use to confirm this major-minor. It's called Alkenes from Alcohols, and we actually carry out this experiment. But it also confirms something else. We can do gas chromatography and look for these molecules. Note that if the 1,2 shift didn't happen, that if base attacked that guy, the only beta hydrogen on this molecule is off the methyl, and the only alkene you could get would be this one. And note this alkene is completely different structurally from the other two alkenes. So if we actually conducted this experiment, we could research several questions. One, for example, we could look to see if there's any of this alkene. See, if this alkene forms at all, the only way it could form is if the 1,2 shift was slower than base attack. Now, I have taught in this course that 1,2 shifting is fast because it's intramolecular. It doesn't require a molecular collision between the base and the hydrogen, so it's much faster. But it's not really the case. Experimentally, we can go and search for this molecule. If we don't see it, it means rearrangement was real fast. We should see only these two guys. Does molecular collision compete? That's a question we could ask. Also, we can confirm whether the Zaitsev rule really applies. Is the more substituted double bond really major? We can actually, in fact, calculate by how much. So there are nice experiments designed out there to confirm whether this really occurs. Our last reaction mechanism, and I'm not going to do it stepwise, is that of the case for tertiary alcohols. And we can use tertiary alcohols and carry out the same E1 mechanism. It's exactly the same. For example, we could use tert-butyl alcohol. React it with an acid to protonate it. So you might use H2SO4 again, or H3PO4. You can even use Lewis acids in these. Tertiary produces substituted double bonds, and so reacts very quickly. And you can get away with lower temperatures the more reactive it is. Remember, when I use a triangle, that just means heat. I'll always give you the triangle, but it means enough heat to cause the elimination. In some cases it'll be several hundred degrees. In some cases it'll be near room temperature. Minus H2O, great leaving group. And we get the tert-butyl carbocation. Now we can pull off a beta H. All of the methyl hydrogens are beta H's. Pull an H off any one of the methyls, you get the same alkene. So my base in this case would be HSO4 minus, because the proton was added. Pulls the proton off, and we could get, for example, CH2 double bond C, CH3, CH3. Excellent. Well, that's dehydration of alcohols. We also can carry out reactions with alkyl halides. In this case, we pull off hydrogen, so it's dehydro, and we pull off a halogen, so it's dehydrohalogenation of alkyl halides. Now, I've already alluded to the differences between alcohols and alkyl halides in elimination. Unlike alcohols, which go E1, all alkyl halides go E2. So if I take a molecule like, I don't know, CH3, let's make it a long chain. CH2, give 6 CH2 groups in a long straight chain. And another CH2 and a Br. That's one bromooctane. If you hit this with base, a powerful base, how about let's hit it with terbutoxide. We learned that this is a weak nucleophile powerful base. Do you remember why it's a weak nucleophile? Terbutoxide is sterically hindered by the methyl groups. So it's not good for nucleophilic attack. It can do it on unhindered carbons, but typically it's better as a base. So if I react these two, this goes E2, anti-periplanar elimination. E2. Takes quite a bit of heat for the primary to undergo the reaction. This is for a primary alkyl halide. What about secondary alkyl halides? Well, let's try 2-bromopentane. Bromopentane. Secondaries go E2. You need heat to drive this reaction. And we can use a base. What base should we use? How about sodium methoxide? If sodium methoxide is my base, what solvent do I dissolve this salt in? Always use the conjugate acid of the base you're using. If methoxide's my base, use methanol. Why? Well, if I dissolve methoxide in water, methoxide's going to react with water to produce hydroxide. I won't have any methoxide left. But if methoxide deprotonates methanol, okay, so my solvent is methanol, then I just get methoxide back. And I always have the methoxide. So my base will be this. What do we form? Well, we form quite a few molecules. And let's give some percentages on this reaction set. Here. If I pull a proton off here, I get 2-pentene. Now, just so we don't forget, I am going to draw both stereoisomers. So here's the cis and the trans. Now the percentage is typically 51% trans and 18% cis. The total amount of 2-pentene, therefore, is 69%. The other molecule that forms is when this carbon's beta hydrogen is pulled off. And of course, if you draw that, you get 1-pentene, which forms at 31%. Why is 1-pentene only formed at 31% and the 2-pentenes are formed at 69%? Well, 2-pentene is more substituted. There are 2 carbons off the double bond, a methyl and an ethyl. Whereas 1-pentene only has the propyl group off of it. The 2-pentene is more substituted, more stable, and according to Zaitsev, it is the major product. The reason I've drawn cis and trans here is to point out another interesting observation, though. Notice that the trans predominates significantly over the cis when you form 2-pentene. This is very important. Why does this occur? Well, the bulkiest groups are the ethyl and methyl. And when you are cis, the ethyl and methyl are close proximity, and this produces greater repulsion. The greater repulsion creates higher energy. So when the double bond actually forms, less molecules achieve the cis orientation as opposed to the trans, because the trans gets the bulky groups further away and reduces the steric hindrance in the molecule. All right. Also going E2 is tertiary alkyl halides. So if you take tert-butyl bromide, just like we did with tert-butyl alcohol, of course we don't require protonation because we've already got a good leaving group. We hit this with, say, sodium ethoxide. The solvent, what solvent would you use with sodium ethoxide? Oh, of course, you'd use ethanol, the conjugate acid of the base. Now, I will put heat here, and I will admit that this elimination occurs at very reasonable temperatures. In fact, it probably would even occur at room temperature. But remember, triangle in my course means enough heat for elimination. And that heat could be room temperature. So we'll put in enough heat, whatever heat's required, 60, 50 degrees Celsius, whatever heat's required to favor elimination. What's the difference between this tert-butyl bromide and tert-butyl alcohol? Tert-butyl alcohol went E1. This guy goes E2. So we look for anti-periplanar elimination. The base will come in, grab a proton off here, make the pi bond, and the bromine will leave, all in a single step. And you will get your alkene. So in actual fact, the preparation of alkenes has already been covered in alkyl halides and alcohol chemistry. Excellent. Now there are other ways of preparing alkenes. For example, I can carry out reduction of alkynes. Now we're going to look at this more closely later, so I'm going to just very quickly give you the reaction and leave it at that. We'll come back to this reaction later on. But I can take any alkyne in the presence of 1 mole of H2 gas. So it's a 1-to-1 reaction. H2 gas, but I've got to make sure there's no excess because this reaction won't stop. So I've got to make sure I use only 1 mole or 1-to-1 stoichiometry. Okay, and I need a catalyst. And the catalysts are either nickel or platinum or palladium. These are all metals in the same group in the periodic table, and they have a unique ability to act like a sponge with regard to hydrogen. Now, sponges, everyone's familiar with a sponge. If there's lots of water around and the sponge has soaked up a lot of water, you can use a sponge to deliver water. You can pick up the sponge, wring it out, and lots of water will come out of the sponge. And so when there's hydrogen gas around, nickel, platinum, or palladium acts like a sponge to the hydrogen. It activates it as a catalyst and can deliver that hydrogen. The same way you can squeeze water out of a sponge, nickel, platinum, or palladium will deliver the H2 gas to the molecule. And if you have just 1 mole, you will get alkyne. Okay, so we will get alkyne. And in this case, you get a mixture of cis and trans, and the trans would predominate. So I'll draw it trans. But the H adds on to the triple bond. The problem with this is you can't stop it. It's tricky. If there's any more H2 gas, the sponge will keep delivering the hydrogen and you'll get alkane. But we don't want alkane. We're making alkenes. We don't want alkane, so we want to stop it. So you make sure you use only one more of H2 gas, and that can be difficult. There are also catalyst cell, special catalyst cell. Let's do this. We'll look at those special catalysts later on. Likewise, though, these metals are like sponges. What if there's no water around? The sponge is dry. We have a dry sponge. And there's a water spill. The sponge can scavenge the water, soak up the water, pick it up. The quicker picker-upper. Removing the water. So if I use nickel or palladium or platinum, any one of them, I don't use them all, I use one of them, and heat, in the absence of hydrogen, the nickel, palladium, platinum will start grabbing the hydrogen off the alkane. And it is possible for it to scavenge both hydrogens and go right through to the alkyne, so you have to be careful. But we can scavenge hydrogens off alkane and make, once again, alkene. Okay, so we get some very interesting reactions taking place using the catalyst nickel, palladium, or platinum. How do we prepare alkynes? Well, we prepare alkynes from what are called vicinal dihalides. What does vicinal mean? Well, if we're looking at a carbon framework of two carbons, if the halides are off, let's say bromides, are off with the same carbon, they are referred to as geminal dihalides, or in this case, geminal dibromides. Geminal, coming from Gemini, meaning twins. Geminal means the bromines are off the same carbon. If we say vicinal, we mean the bromines are off neighboring carbons. We get vicinal from the same place we get the word vicinity or locality, local vicinity. Nearby carbons, neighboring carbons, we use vicinal to refer to these. So when I say a vicinal dihalide or a vicinal dibromide, I mean like what we've been calling a 1,2 diol or 1,2 dibromo adduct. So vicinal is just another word that can be used for this type of description. Let's take a look at a reaction then. I can take alkene. And in a reaction we're going to examine later of alkenes, I can react this with Br2. If I react this alkene with Br2, I will produce an alkane which has vicinal dihalides. How does that get me to an alkyne? Well, it turns out elimination reactions can be used to generate alkynes, because we can do elimination in base. We can take this guy with a powerful base, and remember our friend sodium amide, A and A, NH2. NH2 was NH2 minus, which has 2 lone pairs. Ammonia is a powerful base, but if you deprotonate ammonia, you get 2 lone pairs, and you get a negative charge. NH2 minus is a far more powerful base than ammonia. Sodium amide, super powerful base. If we're using a base like sodium amide, what's my solvent? Do I dissolve it in water? Obviously not. The NH2 minus would deprotonate the water. I'd end up with hydroxide. I'd have no NH2 minus left. What's my solvent? You use the conjugate acid of the base. What's the conjugate acid of NH2 minus? NH3. But NH3 is gas. How can you use that as a solvent? Well, we have to cool it down. We might use acetone with dry ice, carbon dioxide in it, and that will change the NH2 gas into NH2 liquid. And then it can be used as a solvent. Liquid ammonia, a bowl of it in an acetone dry ice bath. The acetone dry ice will be at minus 78 degrees Celsius. And that's enough for the ammonia to remain liquid. Take sodium amide dissolved in it, and what's going to happen? Alkyl halides go E2. This NH2 minus will come in and grab a proton. You get anti-periplanar elimination. The anti-periplanar elimination will just form an alkene, won't it? Well, you're right there. You'll initially get something like this. As one H and Br pulled off, it'll leave behind the other H and Br. And what will happen as electrons are added from the solution, you will get another elimination step where the amide attacks CH, another pi bond forms, and eventually you get to alkyne. It's like a double elimination. It's just like you were doing two E2s, pulling off two HBRs, and you get alkyne. Now, here is the second step that happens. We often have to add, in a second step, acid. What is the acid added for afterwards? Well, the problem here is, what if this H, this R, equals an H? What if this guy were an H? The amide would not just form alkyne. Remember, we learned that amide's a powerful base. It would deprotonate this, and we get the acetylide anion. So we add acid to protonate back the alkyne. It's not a problem if R is a methyl. If both R's are methyls and there's no H off the triple bond, it's not a problem. But if it was an H and you got the acetylide anion, then acid would be needed to protonate in a second step and give you back the alkyne that you're trying to make. Also, acid is used to destroy any residual amounts of amide, remove the ammonia from the solution. So after you get your product extracted out and the ammonia evaporates, H3O plus helps hydrolyze out any base. So the overall reaction is one sodium amide. How else can you make alkynes? Well, as you see, sodium amide can make the acetylide. And acetylide is a powerful nucleophile. If we want to make a different type of alkyne, make the acetylide, and then we can do nucleophilic attack, because we learned that this acetylide is a good nucleophile. So I, for example, could do nucleophilic attack on, pick an alkyl halide. How about propylbromide? Propylbromide's primary reacted with a nucleophile. Primaries go SN2. I'll get backside attack. And I'll get propyl. A new propyl group off the triple bond, because it's a good nucleophile. Note, none of these reactions are new. We're just changing the nucleophile. Another powerful base that I can use on such alkynes, Grignard reagents, like methyl magnesium bromide. Methyl magnesium bromide's delta minus. It'll grab the proton, and you'll get CH4, gas that bubbles out of solution. And you'll get your acetylide. But it'll be like a Grignard. It'll be associated with the magnesium bromide. There'll be a delta minus. Once I get that Grignard, I can react it with many things. All of the reagents we covered in alcohols that you can use Grignards on, you can use an alkynyl Grignard on. Methanol, aldehydes, ketones, esters. When you do an attack, say let's say you have this Grignard, and say we attack, 2-butanol. This reaction will proceed like all the reactions that we have covered for Grignards. If I attack a ketone, the delta minus on the carbon is attracted to the delta plus of this carbon. It attacks, pi bond moves out, and I'll get CH3, C, O minus. Just like usual, the MgBr plus will be nearby. But off of here, I got my C triple bond. CH3. And when I throw in my acid, in my second step, H3O plus, I'll get an alkynyl alcohol. Just standard Grignard. The only difference is I have this guy attacking. So alkynes can be used as Grignard reagents. These acetylide anions can be used attached to Grignard reagents and do all the nucleophilic attacks we've learned. And lastly, of course, there is the reaction with the material that I've already alluded to. We can take Alkane, react it with our catalyst, nickel, palladium, or platinum. The interesting thing is you keep heating it, you can scavenge more hydrogens, and you will get to alkynes. So if you keep the process going, it's really hard to stop it at alkene. You can get alkynes in the reaction in the presence of catalysts. These catalysts, remember, act like sponges, and in the absence of hydrogen, they'll scavenge hydrogen off molecules. In the presence of hydrogen, they'd actually deliver it for reactions. Okay. Next lecture, we're going to actually start looking at how reactions take place on alkenes. What is the mechanistic and reactive pathways taken by the alkene molecules? So this is it for the preparation and introduction of alkenes and alkynes. I'm Dr. Brian Lloyd. This is my Scribblecast. I thank you for listening. Thank you very much.